Buenos días. Le pido disculpas por no hablar español. So I speak in English. No puedo hablar español. Okay. So just as Midwell said, a general view of what we do for wind shear at Météo-France for wind shear observation. And I will first like to thank the organizer for inviting me, because we all have to learn from what we do from others, and I already learned much today, so thank you. Next. Okay. First, I would like to stress the importance of wind shear for air traffic security. I took figures from the IATA safety report, stressing that the fatalities and the accidents are getting rarer, more and more rare, and you can obtain this kind of results by working on security of the aircraft and the training of the pilots, but you can't change anything in the weather. So the risks associated to the weather and to the wind shear, the only solution you have is to observe them and forecast them and share the information. So we follow the IATA recommendation to work on this subject. In France, we have 3 main sites with a specific instrumentation. I will not talk about Charles de Gaulle. It's just an H-band Doppler radar for wind shear in wet condition, in cloudy rain condition. In Nice, the situation, the location close to the sea is quite similar to Tenerife. We don't have trade winds at Nice, but it's a difficult situation. I will show what we do, and we use the airport of Clermont-Ferrand as a test bed for experimentation and research. So here is the view of the Nice airport. What's important is the number of passengers and the number of movements. It has a great economic importance, but as you will see, the situation is quite difficult. The coastline is not straight, so you have converging and defluing areas for the breeze. But by luck, sea breeze is not so high, so I don't think that's the main problem. We also have hills nearby, so this is a vertical cross-section. You can go from 1,000 meters to 0 in about 13 kilometers, which creates eddies, undulatory flows, non-uniform wind fields. There is also this valley, the valley of Var River. You see at about 10 kilometers inland, it's well marked with mountains around at 1,000 meters and a well-marked valley. So we have a clear outflow when the cold air at night goes down, and on the contrary, it favors inflow breeze at the end of the day, which is more important because the maximum wind speed specific to the valley is higher than general breeze speed. And then, in general, we have higher mountains not so far, 3,000 meters at 60 kilometers, and generally it's a convection-prone area, and where wind gusts happen quite often. So, and there is a specific phenomena in Nice, which is called la renverse. In fact, there are moving eddies which occurs around Nice, and they can move quite fast, which create wind changes, which then change direction from east to west quite fast. The main typical situation is a strong wind situation and a synoptic wind from southwest, but it can also occur in other situations. So it gives you a situation like this, which happened this year in March. An aircraft coming, I think it came from Paris, preparing its approach, and okay, the wind has changed direction, so I will land in the other direction. So what's specific to Nice is that difficulties must be anticipated quite far away, because you see it's quite a complicated approach trajectories to avoid the capes around Nice. Most of the flight arrivals are in this direction, but some are in the other way, of course. And the missed approach point is 11 kilometers away from the runway. So it's better for everybody, for the pilots, the air traffic controller, and so on, if we have information at that distance, which is quite challenging for a wind observing system. So the decision was taken to have complementary measurements based on the teledetection, an H-band Doppler LiDAR, which is efficient with cloud and rains, and a LiDAR which is blind when there are clouds, but which can measure in dry condition. So I want to stress again on the need for a fast refreshment rate of the information, the fast-moving wind shear that we are currently working. I will explain this later. We are currently working on the installation of the LiDAR. It's not yet installed, but there has been an experiment in the past. This was in 2009. There was a LiDAR in Nice, and that's the wind field. So the LiDAR only showed the direction, the wind speed in the direction of the light. So this typical, you see here a wind coming this way, the general wind flowing this way, with a small opposite direction at the end of the range. And this is only 4 minutes later, and 4 minutes later, the opposite direction has moved some, I think something like 3 kilometers. So we need a high refreshment rate of the observation. So these are the characteristics of the H-band Doppler radar, which it's a radar from Selex, which does PPI, just as Maria explained, at different elevation, and also RHI on typical direction, the same as the LiDAR, I will show later. So this is an example of the observation we can get. Here the radial speed and the convergence line, this corresponds to this position close to the airport. With the reflectivity, it was rainy. And on the RHI observation on the plane along the Var Valley, you see clearly the downflow, the flow in one direction and then another in the other direction. This radar is operational. It's the base of the wind shear warning messages that the Meteo service sends to the air traffic control and then to all the pilots. It's still considered experimental, but it's renewed from year to year. So I think we can consider it almost operational, but it's only in rainy situation. So we have the plan to complete this system with the LiDAR, with high specification. We would like to have it really available most of the time. We see again the 11-kilometer range with a high with a high refreshment rate of the data. So, of course, with the LiDAR, you can't have high range every time. So these are the conditions with normal visibility, no rainfall, something like that. And so this is the plan we have for the scanning. So one turn, 1 ppi at 3 degrees, and 3 vertical scanning RHI in the direction of the runway and in the direction of the Var Valley. So it's been a long project to do that. I think we're getting close to it because the decision has been made. We've chosen Mitsubishi LiDAR. The contract has been notified. We plan to install it next year in April. We have a very short slot for doing that before the winter, before the summer season. Where are many flights, and after some work on the runways. The year 2009 will be a year of testing, validation, and we hope it will be operational in 2020. So let's jump from Nice to Clermont-Ferrand. Some of you may not know Clermont-Ferrand. It's less famous than Nice. It's in the center of the France. It's close to the Puy de Dôme, the Massif Central mountains. The situation is not so different from the one you have in Bilbao, I think. The airport is in a valley with the mountains nearby. The valley is larger than Bilbao. The orientation of the runway is not the same, but it's quite similar, I think. We have very different wind flows in the valley from, this is wind rows, which shows mainly weak wind from north to south or south to north. And on the Puy de Dôme, you see mainly westerly winds and a little bit of southerly winds. You have also some hills nearby, which creates eddies when the wind flows from the south. And the economic importance of Clermont-Ferrand is much less than Nice, of course, much less passengers, much less movements. But it's a very interesting situation for research, for learning more about what happens in these conditions. So we have been working on this airport for a few years now. So this is a more detailed explanation of the typical wind shear situation. So, two kinds of situation with southerly winds, general synoptic southerly winds, and eddies provoked by the hills there, and with a different sense of rotation. Or you have the strong westerly winds flowing upward, which creates below the mountains turbulent wind, generally on from south or southwest direction, and there is a level at which there is a strong shear. So here are some details about the field campaigns. We have, at Clermont-Ferrand, we have installed a vertical wind profiler in the beginning of 2017, and it's still operating. We have installed 2 Doppler radars at the end of 2017, and we have just taken them away. One is just a vertical pointing LiDAR, just to give a profile, just at a profile, UHF profiler, and one is a scanning radar both are from Leosphere. There have also been a microwave radiometer. Doesn't give any information about the wind, but gives humidity and temperature profiles, which are important to document the vertical profile or inversion, eventual inversion, and some additional station around the airport. This is just an example of view from the LiDAR with a vertical stands in a different direction, where we can clearly see layers of opposite direction and undulatory phenomenon. This experiment at Clermont-Ferrand was also used as a technological test bed. The idea was to use the UHF Doppler radar, usually pointing vertically or just at a few degrees from the vertical, and to see if, by putting the antennas in the direction of the approach slope, we could get information from wind shear. This is quite a challenge. This has been going on for many years now because you have many side lobes of the antennas. The back signal from the air or from the turbulence is low comparing to the signal from the side lobes of the antennas, which can be the ground or cars or all kinds of things. So the manufacturer of this radar is now abandoning this kind of antennas for this test, and is testing a parabola. This is not the exact parabola, it's just an illustration, of course. It's much smaller. And we are currently developing with other research lab in France signal processing technique to kind of filter the unwanted signal and to detect wind shear. But this is quite, as I said, it's quite challenging, and we don't hope results in the next months. Last thing, in Clermont-Ferrand, we are using the data we collected last year to test our forecast capabilities. What I illustrate here is just the impact of the model resolution. We are using AROM. The operational resolution is 1.3 kilometers, and we have a test version at 500 meters, which clearly is able to describe much more accurately the undulatory phenomena. And the current studies are about the impact of the additional information. The UHF profile, simply the vertical profile given by the UHF profiler does it allow models to have a better forecast. We are planning to test modest data received from aircraft in the next months. It's a pity in Clermont-Ferrand there are no AMDAR reporting aircraft that land at Clermont-Ferrand, so we don't have AMDAR information. But imagination is the limit, and we will test other kind of new types of observation. And that's all. And